I've been involved in nuclear safety research since 1974. Most of my career was spent at the Idaho National Laboratory here in Idaho Falls. And then in '96, we started innovative systems software to develop thermohydraulic and severe accident simulation software. I've been involved in severe accident research since the accident at TMI-2 in 1979, and been involved in code development almost as long. The activities in severe accident simulation that I currently direct is an international cooperative program called SCDAP. We have more than 70 organizations around the world. We're currently involved in activities in over 30 countries, and we develop a number of computer codes, including specific codes that can be used for severe accident simulation, including RELAP SCDAP-SIM, which I'll spend most of the time in the lecture talking about, SAMSON, which is developed in Japan, and also a desktop simulator package called RELSIM, RELAP SCDAP-SIM. Okay. As shown in this slide, RELAP SCDAP-based codes, including our version of the code RELAP SCDAP-SIM, has been used for more than 30 years to support severe accident research programs, including most recently we have been actively involved in the assessment to support the Fukushima Daiichi activities. RELAP SCDAP-based codes have been used in the design and analysis of all major in-vessel severe accident experiments. I'll just give you very quickly a few examples of results from those to get started. It was the primary code that was used to support the TMI-2 accident evaluation in core and vessel examination, and our calculations were the first to predict molten pool formation and the relocation of melt into the lower plenum in TMI-2. We became involved in Fukushima Daiichi immediately after the accident. I served as a technical expert for the IAEA emergency response team, and we were able to do the first set of detailed calculations for Fukushima using RELAP SCDAP-SIM, where we predicted the melting of the fuel and likely vessel failure for the Fukushima Daiichi units 1 through 3. Now let me just say a little bit about the codes within our group, our cooperative development group. The specific codes that we're developing are part of the SAMSON family, which was developed primarily in Japan, and RELAP SCDAP-SIM, which was developed here originally in the United States. These codes have a series of modules and packages that treat the entire behavior of the reactor system during the severe accident. The items which are outlined in green are the items that I'll focus on during this presentation, which are the codes that describe the in-vessel phase of a severe accident. That's covered with the RELAP SCDAP-SIM code. Those items shown in yellow are those behavioral processes which are important for the containment response. These codes are being used actively in Japan, and they will play a key role in the Fukushima assessment and cleanup activities. There are a number of activities that we're doing that's associated with Fukushima. In particular, we will be continuing to assess the state of the core, the vessel, and the containment using a combination of RELAP, SCDAP-SIM, and SAMSON code modules. We will look at the thermohydraulic boundary conditions and ultimately, hopefully, provide guidance to TEPCO and others so that they can safely remove the damaged core and damaged fuel. SAMSON was a very detailed code package that was started in Japan in the 1980s. And it was developed for approximately 15 years, and then that work was considered completed, and that software was mothballed. And now that package and that model development activity is underway again by the Japanese government. In addition to the co-development activities to support Fukushima, we've established a severe accident simulation center at the University of Tokyo, where we're continuing to do model development both on RELAP, SCDAP-SIM, and SAMSON. One of the questions that we get asked in the development of these very detailed best estimate codes like RELAP, SCDAP, and SAMSON is, why do we need such detailed best estimate codes? Well, the answers are really fairly simple. Severe accident behavior is complex. When we talk about the melting of the core during a severe accident, we're really talking about the melting of a very complex system of materials and structures. These materials in the reactor core melt over a very wide range, starting at temperatures as low as 1,000 Kelvin and as high as 3,000 Kelvin. The lowest melting temperatures in typical reactors are silver, indium, cadmium control elements. They are the first to start melting around 1,000 Kelvin. The last material that starts melting are the ceramic materials, mostly the fuel UO2. The severe accident behavior is also complex because some things that are somewhat unexpected also occur during a severe accident. In particular, one of the surprising aspects that we've learned from many experiments is that the influence of water addition has a very different effect depending upon the state of the core. When peak cladding temperatures are above 1,500 Kelvin, we see accelerated heating and melting. When water is added, once the fuel starts melting, we see very little influence of water addition. Severe accident experiments have also taught us that the presence of air is very significant. All these different processes and phenomena must be modeled in some detail if we are trying to predict the behavior of a reactor core during a severe accident. These detailed best estimate codes like RELAP, SCDAP-SIM are also very important. As I'll talk very briefly about Fukushima, it's important that severe accident mitigation strategies are validated. They're verified against experimental conditions to make sure that they are appropriate and that they are the most efficient in mitigating an accident. In the case of Fukushima, the influence of depressurization was very significant. Whether depressurization occurred or didn't occur has a very strong impact on the timing of the heating and the melting of the core. In Fukushima, water addition, particularly in the later stages in Unit 2, was also a very significant mitigation strategy. So very briefly, I'll just review what we've learned from 30 years of severe accident experiments. Obviously, I can't go into great detail, but let me just tell you about some of the highlights and what we attempt to model precisely with these detailed best estimate codes. There have been a large number of core melting experiments performed since the accident at TMI-2 in 1979. And as shown in this slide, there are a number of things that happen in the core as the core temperatures get higher. If you look at the left-hand side of this slide, what you're seeing is actually a cross-section of a BWR bundle that was tested in a facility in Karlsruhe, Germany at the Karlsruhe Institute of Technology. And if you look at the leftmost picture, you'll see kind of the outline of fuel rods, a control blade, a BWR control blade, the channel box around the control blade, and a surround around the fuel rods. That picture is a snapshot when core temperatures or bundle temperatures are around 1500 to 1700 Kelvin. This is the point where the liquefaction and the failure of the control blades and the channel boxes start taking place. As we move to the middle picture, we're now in the upper range of that 1500 to 1700 Kelvin. You notice if you compare that assembly picture, the channel box and the control blade have completely disappeared. So one of the important things that these experiments have told us is that very early on in a severe accident, one of the first major damage events that will occur in the core is the liquefaction and the failure of the control blade material and channel boxes. This is equally true for PWRs with silver, indium, cadmium control rods. At the same temperature, those structures start to be destroyed. You can also see in that picture we still have quite relatively intact fuel columns and fuel rods, even though the control blade material has disappeared. As we continue to higher temperatures, at temperatures around starting at 2000 Kelvin, 2000 Kelvin is the melting point of the as manufactured zircaloy cladding. That material starts to melt around 2000 Kelvin, and then it can start relocating downward in the assembly over a temperature range from 2000 to 2600 Kelvin. As temperatures continue to climb, as we reach temperatures above 2600 Kelvin to 2800 Kelvin, we start melting and relocating the ceramic fuel. And as you see on this slide, I'm quite specific to use the terminology UZR02 to indicate that this is a mixture of uranium zircaloy that's heavily oxidized, so it's a ceramic material, and that material starts relocating, forming blockages. The pictures that you happen to see on this slide are from French Phoebus experiments that were performed in Cadarache, France, with fresh and irradiated bundles. I mentioned one of the complex events that was somewhat surprising when we started this experiment, or these experiments in the early 1980s, was the influence of water addition. Most of us are familiar with design basis accident analysis, where peak cladding temperatures remain below 1500 Kelvin. Under these conditions, water addition results in the rapid cooling of the core, but as the temperatures go above that, we start to see other responses due to the water addition. This slide's a very complex one, so I'll just spend a little bit of time going through it and explaining what you're seeing on the screen. On the left axis is the water level. This curve or this figure was taken from an experiment that was also performed in Germany called the Quench 11 experiment. And in this experiment, they heated the bundle up If you look at the bottom axis, we have a time scale from 5,500 up to 5,900 seconds. And on the right of that figure is the temperature ranging from 300 up to 2,400 Kelvin. In this experiment, in the first several thousand seconds, they're heating the bundle up, and they heat it up to peak temperatures that are on the order of 300 up to 2,000 Kelvin in the bundle. If you follow this heavy blue curve, that's the water level in the bundle. So by the time that they've heated the bundle up, the water level is quite low in the bundle. It's very close to the bottom of this bundle. And you can look at the range of measured cladding temperatures. They range anywhere from 400 Kelvin up to about 2,000 Kelvin. Then, in this experiment, they reduced the power to 0, so the assembly has the opportunity to start cooling down, and then they start injecting water into the bottom of the assembly. So you can, if you follow that blue curve up, you'll see water moving up into the assembly with time. And if you look at these other curves, the temperature curves, you'll see different responses. Let's just pick this red curve here. This happens to be at an elevation in the experimental bundle of about 750 millimeters, or 3/4 of the way up in the assembly. You can see if we follow the red curve along, as the water is added, those temperatures gradually cool down and gradually quench. You can see temperatures here, 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 and here, which are at lower elevations in the bundle. But now let's contrast that to a thermocouple position that's slightly higher in the bundle. The green curve is at 850 millimeters. At that, we're at a temperature on the order a little over 1,700 Kelvin. And if we follow that green curve, you'll see instead of the temperatures going down, they start going up. If we go to the 950 meter elevation, the 1,050, 1,150, so the upper portion of the bundle that starts out at initial temperatures above 1,700 Kelvin actually heat up when water is being added. So that difference, the contrast between the red curve at 750 and 850, really tells a story about the transition from rapid cool down of an assembly when water is added to one where that assembly is heated up. This process has to be modeled in those detailed codes. Of course, the reason for that heat up process is because of the oxidation of zircaloy cladding and the resulting production of hydrogen. And in this curve, on this figure, we have temperature on the left, again going from 400 up to 2,400 Kelvin, plotted versus time. And on the right, we show the hydrogen generation rate. And you can see here is the quench initiation. So we are producing hydrogen. We are getting some oxidation during the bundle heat up. But as soon as the water is being added to the assembly, the hydrogen production and the oxidation, which is producing heat, of course, is causing the temperatures in the bundle to go up. So as you can see from a very, very quick summary of 30 years of experiments, there's quite complex behavior that occurs during a severe accident. All that information is incorporated in detailed best estimate codes like RELAP, SCDAP, SIM, and SAMSON. It incorporates the knowledge we've gained over the 30 years of severe accident experiments, as well as what we've learned from TMI2. These models and correlations have been widely proven over a series of international validation exercises. These code packages have been tested in international standard problem exercises. In these exercises, different codes, different analysts participate to attempt to predict experimental results. under very carefully controlled conditions. In addition, these models have been used by the international community, by regulatory bodies, research organizations, as well as universities to support their severe accident and other thermohydraulic research activities. One of the other reasons that these detailed best estimate codes are quite useful is that because they have very detailed models and correlations in the code, they are much more easily scalable from these integral experiments in the existing database to new plant designs and conditions. These detailed models, fortunately, are much less sensitive to the knowledge and the experience of the end users. As a consequence, we've found that analysts that have a good fundamental understanding of basic thermohydraulics using these detailed best estimate codes can make quite accurate severe accident simulations, even though they may not have a significant or a strong understanding of severe accident behavior. There are a number of other codes currently used in the world. There's two basic types, these detailed best estimate codes like RELAP, SCDAP-SIM, and SAMSON. There are other widely used codes like MAP and MELCOR, which are more simplified interval codes. And these codes are very useful for safety studies and source term calculations, but they are not we don't consider them good enough for training or the assessment of unexpected conditions. And the reason that these simplified integral codes like MAP and MELCOR are not good enough for predictive or training purposes is that they intentionally ignore important phenomena in order to maintain simplicity of the codes as well as performance of the codes. As a result of these modeling simplifications, these simplified codes rely very strongly upon the experience of the end user and the input model developer. Thus, these simplified codes actually require a lot more expertise in severe accident behavior, a good understanding of the experiments for the user or the person trying to do the simulation to do a reasonable job of calculating the severe accident response. MAP is very successful in terms of its performance standard. It's by far the fastest severe accident code. They have focused their development activities on speed so that they could do very extensive sensitivity studies for PSA or probabilistic safety studies. Both MELCOR and MAP rely upon an extensive use of user-selected parameters in order to allow them to simplify many of the models and correlations in the code. I'll just give you some brief comparisons between these different kind of approaches. On the left of this slide is an example of some of the modeling approaches from RELAP, SCDAP-SIM. For thermohydraulics, we use a quite detailed 6-equation non-equilibrium hydrodynamic model. This is kind of a standard set of models for basic system thermohydraulic calculations, widely used RELAP, TRAC, RETRAN, codes which are widely used in the world for system thermohydraulic calculations. In RELAP, SCDAP-SIM, we have 2D heat conduction. And if you look at the column on the right, this shows basically the same type of basic model in the MAP and MELCOR code. So instead of a detailed non-equilibrium thermohydraulic model, they use a quasi-equilibrium hydrodynamic model, which works quite well in boil-off situations, but doesn't always work so well in more complex thermohydraulic conditions, such as the addition of water. Let me talk a little bit about a very important model. Remember, I talked that from experiments we know that the core materials start melting over a very wide range with temperatures as low as 1,000 Kelvin, as high as 3,000 Kelvin. The reason is you have different materials in the core. You have structural materials as well as the fuel rod materials, and these all have to be tracked and modeled separately if you want to track the relocation of these different materials. In the simplified codes, they simplify the melting process typically by putting in a core slumping user option, which determines when the core slumps. So they simplify and gloss over some of the different melting events. For example, in the detailed codes, grid spacers, we have to model grid spacers because grid spacers have a fairly significant impact on the relocation of molten material and the formation of blockages. We have quite detailed models that describe what happens when the fuel melts and we form large molten pools. In the detailed code RELAP SCDAP-SIM, in the simplified codes, they have a user-defined core slumping, and so you have somewhat simplified description of what happens when the core melts. Now, why is that important? The main reason this is important is because then the user in these simplified codes, really the user determines how and when the core melts down. And as a consequence, depending upon what parameters the user selects when setting up their model or their simulation, these codes may, in some cases, significantly underpredict the melt stored energy and the hydrogen production during the heat up and meltdown of the core. Let's talk about the influence of the thermohydraulic conditions as well. In detailed codes like RELAP SCDAP-SIM, the thermohydraulic flow patterns not only depend on things like natural circulation and the temperatures in the reactor coolant system, but they also depend upon the state of the reactor core. So flow patterns vary in these detailed codes depending on where blockages are formed or molten pools form. By contrast, in the simplified codes, the flow patterns are hardwired using user-defined geometries. The addition of water is a very significant one. I showed you the example from one experiment showing the heating of the upper portion of the assembly when water is added. That occurs over and over again in the many experiments that have been performed where water has been added. We see very strongly this accelerated oxidation, heating and melting at temperatures above 1500 Kelvin. We see as the fuel rod cladding material starts melting around 2000 Kelvin, we find that that molten material can actually oxidize and contribute additional hydrogen and heating to the reactor core. And then as we form large ceramic pools of molten material, we find that the addition of water has relatively limited effect on the cooling of those large ceramic pools. By contrast, the simplified codes don't model that level of detail in the water addition, and in particular MAP has serious limitations when you're adding water in that they don't consider this accelerated oxidation at temperatures above 1500. Again, why is this important? Well, in the case of MAP, these simplified quenching models will predict cooling in the core even in cases where large number of experiments have shown that this accelerated heating and melting may occur. Another area where there's significant difference between these detailed best estimate codes like SAMSON or RELAP SCDAP and the simplified code are those models which describe the retention of debris and melt in the lower plenum of the lower head. And I'll just give you some examples of the different approach. This slide, I'm not going to go through all the details of what's included in this, I just wanted to make the point with this slide that the Japanese SAMSON in-vessel retention models are by far the most detailed physical models of in-vessel retention available in the world today. They're 3D models. They can track the influence of impingement of the melt on different structures in the core, the addition of water on the outside of the vessel. So they are the models that we use if we really need to refine how the lower head will fail. And these models, I think, will be very significant in helping in the cleanup of Fukushima Daiichi. The RELAP SCDAP-SIM code also uses a quite detailed model. You can see from this slide it's a detailed two-dimensional model, has a quite detailed finite element mesh to predict the behavior of the debris and the lower head. It predicts the relocation of material into the lower head and how that interacts with the lower head, and also the influence of ex-vessel flooding. It's simplified relative to the SAMSON code in that it's two-dimensional, so it can only treat axisymmetric representation of the debris in the lower head. By contrast, the Melcor and the MAP models are quite simplified relative to both the RELAP SCDAP-SIM and the SAMSON package, and as a consequence of these simplifications, for example, as I've shown in this slide, the coarse nodalization used in Melcor makes it very difficult to give an accurate estimation of the heat transfer from the debris to the vessel wall. A MAP simplified stratification model is significant in that it can significantly underpredict the heating of the vessel wall if their assumed configuration of the debris in the lower plenum is incorrect. One of the really important points I want to make about the use of detailed best estimate codes versus these simplified codes is the simplified codes make very extensive use of modeling parameters to adjust basic processes. So therefore, the user and the knowledge of the user that's setting up the models for MAP and Melcor really have a very strong influence on the outcome of the calculations. Because the user has such a strong influence of how the code predicts the state of the core during severe accident, typical validation approaches where people compare the code calculations to data is not really applicable, because the users have the freedom to select one set of parameters to look at one experiment, change those parameters to look at another experiment, and change them again to look at the full plant. So these modeling parameters aren't necessarily scalable from the small experiments up to the full plant. And some of these parameters may not be selected based upon physical phenomena or experiments, but unfortunately may be selected by the user because they have a certain desired outcome for their calculational results. So this combination means the user has a very strong impact on the calculational results in the simulation when you're using these simplified codes. So to close the presentation, I just want to leave you with the idea that these detailed severe accident codes and models we believe will play a very important role in preventing and mitigating other future severe accidents. We've been working with our colleagues in our cooperative development program to set up regional university-based severe accident training centers so that new nuclear engineers are exposed to accurate severe accident simulation. These detailed codes and models will be helping us over the next few years, I think, fully implement what we're going to learn from Fukushima as they examine the core and the vessel. And then finally, these detailed best estimate codes actually because of the computer technology, even though they're quite detailed, can also run significantly faster. So consequently, we are at many of these severe accident training centers, we have desktop severe accident simulators which can be used then to validate full scope simulators with more simplified severe accident models and codes. So that concludes my formal presentation. So I look forward to any questions that you might have, and we can discuss them now.
Perfect, Chris.
To you.
Thank you so much. We have actually some questions here that I would like to put on, well, let's say on the table. And and this question is coming from Japan. Someone from a Japanese authority, and it's like they want to know if actually can the actual codes and simulators to help live on an emergency of a severe accident real situation?
I believe they can. The key is preparation. In the case of Fukushima, we were very fortunate that one of our members, the regulatory body in Mexico, was doing severe accident simulations with RELAP SCDAP-sim for their Laguna Verde BWR. So immediately after the accident, they were able to provide us their full plant model for their BWR, which then we were using to do a series of sensitivity calculations for the IAEA immediately after the accident. With this model, we were able to do the first calculations within a few days of the start of the accident, predicting the state of the core and the vessel. So with preparation, that means you have to have models that represent the plant. You have to have those models available. You have to have people that are trained to use those models. But certainly if you have that in place, the codes are fast enough that we can do calculations as the accident is progressing.
Perfect. We have a second question, and it's actually related to Fukushima, Chris. And it says, looking back at what happened in Fukushima regarding severe accident simulation, what direct actions needs to be taken or have been taken already in nuclear power plants around the world?
Well, I think as most people are aware, the regulatory bodies have asked the utilities and vendors to take a close look at their plants and modify their procedures and trainings to improve the prevention of future severe accidents. For example, from Fukushima, pre-positioning power generators so that they can rapidly move those generators in the event, like Fukushima, that the emergency generators were destroyed. For our part, through our cooperative program, what we're moving ahead for is develop, we think, better training programs. We've decided that the universities are a good place to implement these training programs with the idea that we will expose new engineers as they're moving up and first starting out. We'll expose them to severe accident simulations so they understand the consequence of their actions or interactions during a severe accident. We found, I think, one of the conclusions from Fukushima is these accidents are very rare, and it's difficult to maintain a high level of expertise because people that are expert in severe accident behavior, you know, in 20, 30 years, they are promoted, they move on, they're replaced by new people. So you continually have to replace that expertise, I think, and we think the universities are a good way to make sure that we have a continuous group of people that are very comfortable, that they understand what goes on in severe accidents, and because of that, they can not only help to prevent them, but in the event they do have a severe accident, they're better prepared to help mitigate those accidents.
From the University of Idaho, they want to know approximately how many young engineers under 30 are skilled in RELAP, SCDAP, and severe accident analysis.
I don't know the exact number. We have trained over the last 5 or 10 years a lot of students. I would say in the order of maybe 100 to 200 people have been trained in severe accident behavior. So we have a really good start, and we're continuing to work with a lot of universities around the world. We have actually 20-some universities that we work with around the world, and we're seeing more and more students get involved, not only in analysis, but the developing of new and better models.
Okay, we have another question. This time is coming from Spain, and is basically, do you think that RELAP SCDAP is validated enough not to cause negative training?
I believe so. The code, of course, we've been developing these models and correlations for 30 years. We've applied the code to all the severe accident experiments that have been performed in the world. We continue to use the code to help design these experiments. The code has been used in many blind calculations. By blind, I mean they run an experiment, but they don't release the experimental results. People take about a year to do calculations to show how well they can predict these experiments. And RELAP SCDAP has been widely used in many of these international standard exercises. So we're quite comfortable that the code describes quite well what we've learned from the experiments. We were quite confident in our calculations for Fukushima, and so far our predictions have been proven to be quite reasonable. So I would say the code is as validated as we possibly can for such difficult circumstances.
Okay, a question from the US, Chris says, most training simulators don't even benchmark their non-severe transient scenarios. Melcor and MAP are getting installed on a lot of simulators around the world. Have you been asked to benchmark any of those simulators with RELAP SCDAP?
We haven't personally been involved, but one of the reasons we are training universities and working through the universities is we believe that university professors and students will be asked to help validate these more simplified codes, and we certainly hope that is the case.
Three more questions. We have these questions coming from Italy. Can you tell us some things about the CFD models and their use in combination with RELAP SCDAP?
The main CFD models are used for very specialized situations. For example, we work very closely with the Japanese in their SAMSON code development. For hydrogen mixing and combustion in SAMSON, they use CFD-based packages to try to predict hydrogen production. Some of their models in SAMSON, they're 3D models that are looking at molten pool behavior or CFD-based. So you see more and more of these kind of models, but so far, because of the performance issues, they're limited to special issues where runtime is not such an important consideration.
Perfect, Chris. Thank you. We have this almost last question from Spain. It says, okay, according to your presentation, it looks as if codes like Melcor or Aztec are practically useless. It is hard to accept that after nearly 30 years of development. Could you please comment on that?
No, I think that's far from the situation. These codes are very useful. They are useful particularly for probabilistic safety analysis, looking at different accident sequences to see what influence that might have on the core melt frequencies. So I think they are quite useful. They just need to be complemented by these detailed best estimate codes. So what I tried to explain is where are some of these more simplified codes, where do they have some weaknesses, where users have to be cautious and look to either the experiments or look to some of these more detailed best estimate codes to help qualify the input for these codes and models so that they do a reasonable job. So they're certainly not useless. They have a very important role to play, but you have to be aware of their limitations and be aware of some of these issues where they may give inaccurate results.
Okay, Chris, and the last question here, also from Spain. You have stressed the user effect in severe accident codes as it didn't affect to codes like R5 when it really does. Can you elaborate a bit more on this idea, please?
Well, all codes are impacted by the experience of the user, no doubt about it. That's why we have very extensive training programs to try to improve the level of experience of code users. But for severe accident conditions, what we've intentionally tried to do is through the use of very detailed models, we remove a lot of modeling options from the users where they could make mistakes. And so we try to minimize the user effects as best we can, but still you can certainly tell the difference between the inexperienced users and the more knowledgeable users.
Perfect. So I guess there's no more questions. Thank you so much, Chris. It's been a really good presentation. Overall, we had delegates and assistants from all around the world.